Okay, we are going to continue with chapter 3. This is a chapter where we study about fluid flow. So in this chapter, all the study that is done here is based on fluid dynamics. Okay, from what we learned from chapter 1 and chapter 2, those chapters are based on the idea of fluid statics, but right now we are dealing with the idea of fluid dynamics. So what's the difference between static and dynamics? It's just the idea of dynamic means that the fluid is flowing. Okay, so when the fluid is flowing, it flows at a certain velocity. So the velocity will play an effect towards the calculation on pressure and also force. Okay, so in this fluid dynamics, the main parameters that will be covered is velocity. Number 2, pressure. Number 3, elevation. And I think these 3 will be the main idea for chapter 3. Okay, and sometimes when we are learning about chapter 3, people also call chapter 3 also as the Bernoulli equation. Right, but we are going to go into that later. So now I'm going to go with chapter 3, fluid flow, the introduction. Okay, so in chapter 3, what we are going to learn is the idea of fluid flow in terms of fluid dynamics. And fluid flow is dependent on 3 different physical laws. Okay, the law that we are talking about is number 1. It's called the law of conservation of mass. Okay, number 2 is right. Let me think. Okay, number 2 will be the law of the second law of motion for Newton. Okay, so we call it as Newton's second law. And number 3 will be the idea of first law of thermodynamics. All right. So these 3 laws will be the main laws that we are going to use for chapter 3. The law of conservation of mass will involve an equation called as continuity equation. Okay, and then second law we'll talk about momentum equation, and the first law of thermodynamics will talk about the energy equation. Okay, and in terms of the idea of continuity equation is talking about the mass balance. Okay, momentum will talk about momentum balance. And also on energy equation is talk about energy balance. Okay, so what does it mean by balance over here? Mass balance, momentum balance, or energy balance? It means that if you have 2 points in a system, okay, so if you have 2 points in a system, for example, point 1 and point 2, and piping is moving from one point to the others, okay, the 3 balance that you have over here will be in chapter 3, will be covered over here by this point 1 and point 2, meaning mass balance means that the mass at point 1 should equal to the mass at point 2. Momentum balance means that momentum is the same for each side, and also energy balance means energy at point 1 should equal to energy at point 2. Okay, the momentum balance can be F point 1 should equal to F at point 2. Alright, so that is the meaning of mass balance, momentum balance, and energy balance. Okay, for our study in chapter 3, we will cover all these three equations and all these three physical laws. But we will cover it in terms of, this will be covered first, continuity equation. This will be covered later at number 2. And this one will be the last one to be covered, momentum equation. So we are going to learn continuity today and energy equation. And then we will have the momentum equation later on. Okay. So in order for us about continuity equation, so we are going to learn about the law of conservation of mass. Okay. So the conservation of mass, the law of conservation of mass involve three different parameters. Okay. Number one is called Q. Okay. Denoted as Q, or we call it as volume flow rate. Okay. So Q equals to volume flow rate. So what is this? Is actually volume of fluid flowing past a section per unit time. So for this one, volume flow rate can be denoted as Q, and the unit for it is actually meter cube per second. Okay. And how to get Q over here? It is equal to A times V. A is the surface area of a certain pipe, for example. V is the velocity. Okay, so area should be in meter square, and velocity should be in meter per second. So when we multiply both unit, we'll have meter cube per second. Number 2, we have M, not over here, is called as mass flow rate. Instead of using volume as the calculation, so we use mass, and the unit for it should be kilogram per second, and the mass flow rate actually equals to rho Q. Okay, rho is density in kg per meter cube. Okay, and Q should be equal to this one up here, or we can rewrite it as rho AV. Okay, and the third one will be called as weight flow rate, or W. Okay, W dot, for example. It is actually equal to okay. All right, so the weight flow rate should be equal to this one is kg per second, so this one should be Newton per second, and it should equal to rho GQ. Okay, or it can also be gamma Q, or it can also be rho times G times A times V. Okay, so G over here is 9.81 meter per second square. It means whatever that you have for the mass flow rate, because to change from mass into weight, you multiply it with 9.81. So it means over here, the difference is just the multiplication of G. Okay, so these three will be the mass that we are talking about in this chapter, and this is considered as the main parameters used for conservation of mass. We have Q, we have mass flow rate, and also weight flow rate. Q is volume flow rate. Okay, so here what we are going to do right now is we want to understand the idea of the principle of continuity. So continuity equation is an idea where we have, for example, a continuous pipe like this, moving from one point to another point continuously. We don't have any opening or any addition of application over here. So this should be point number 1, and this might be point number 2. Okay, and the fluid might be flowing like this, and we have the flow of fluid inside like this. Okay, so what happened here is the idea of what we call as principle of continuity is telling us that whatever mass flow rate that we have at point number 1 should equal to the mass flow rate at point number 2, meaning whatever liquid mass that we have over here must be transferred to this side with the same amount. Okay, so it means in this equation we can say rho Q is equal to rho Q2. Rho Q1 is equal to rho Q2, or we can say rho A1 V1 is equal to rho A2 V2. Okay, so it doesn't happen to mass flow rate only. It can also we can also say the same thing for Q. Q1 should equal to Q2, and weight flow rate 1 should equal to weight flow rate 2 also. Means whatever that we have here, okay, should be transferred to the other side with the same amount, because for our study, it's assumed that we don't have any losses in terms of liquid loss to the surrounding or heat loss to the surrounding. So whatever that we have at point 1 should travel at point 2. Okay, so what it means that flowing here from one point to another point, we might have a different velocity from point 1 and point 2, but the total mass flow rate and volume flow rate should be the same. Okay. Any question right now?
No, sir.
No. Okay. So this is valid for all fluid and liquid. Okay. Everything here that you see, m dot 1 equals to m dot 2, Q1 equals to Q2, weight flow rate 1 equals to weight flow rate 2. It valid for gas and also liquids. Okay, so this idea over here will be very important in our study, because this idea will help us to understand very basic idea of velocity difference between point and point 2. Okay, because at point 1 you will have A1 V1, at point 2 you will have A2 V2. Okay, so let us do an example, assuming okay, have A1 to be 0.05 meter, and then you have A2 to be equals to 0.02 meter, and then velocity at point 1 is equal to 10 meter per second. Okay, so if you want to find out what is the velocity at point 2, okay, we can actually do some calculation based on these three equations over here. Okay, the easiest equation that we can use is Q over here, because Q is the simplest one. We say Q1 is equal to Q2, which is A1 V1 equals to A2 V2. So to find out what is V2, it is equal to A1 V1 divided by A2. Okay, so to find out A1, this we can just put it A1 equals to meter square, and this one is meter square. Okay, so to simplify the calculation, V2 should equal to A1 0.05 divided by 0.02 multiplied by V1, which is 10 meter per second. Okay, so we should get the answer for V2 is equal to V2 should equal to 25 meter per second. Okay, so this is an example on how to find out V2. Okay, let me allow the others to get into the class. All right. Okay, in case that is the question, what is V2? For example, question number 1, what is V2? Okay, question number 2, maybe they ask us what is the volume flow rate, Q. Okay, so to do an example, it's just simple. You can use either Q1 or Q2 if people ask you what is Q for this study, because whatever Q that we use will represent the Q inside the system, because both of the Qs are the same. Okay, so for example, this is the answer for question 1. To find out V2, maybe we can find out number 2, what is Q. Q, we can just use A1, V1, because over here A1 and V1 is given in the study, so it can be 0.05 times 10 meter per second. So we have 0.5 meter per second. Okay, meter cube per second. All right, number 3, maybe they will ask you what is mass flow rate. Okay, so number 3, the mass flow rate should equal to rho times Q, or rho times A1, rho times Q, or it can be rho A1 V1, and it can also be rho A2 V2. So if we can use rho times Q, we can just use rho for this question, assuming this is just water, for example. So the rho of water is 1000 kg per meter cube. So we can just use 1000 times what we have here, 0.5. So the answer should be 500 over here, mass flow rate, kilogram per second. Okay. And the last one should be what is the weight flow rate. Okay, so the weight flow rate, maybe we can do simple calculation over here. Weight flow rate is equal to rho GQ, okay, or rho G A1 V1, for example. So we have the Q over here. rho times G will be 1000 times 9.81 times the 0.5 here. Okay. So weight flow rate should equal to 4905 Newton per second for weight flow rate. Okay. So I think we covered every calculation for every balance that we have in terms of mass balance. Okay. Any question?
No, sir.
No. It's quite okay, right? It's quite basic for this one. So this is the first part of our study. Okay, so this, whatever that we do right now over here is called as conservation of mass, and we also call it as continuity equation. Okay, so conservation of mass, continuity equation is this one here. Okay, this part is called as continuity equation. The m dot 1 equals to m dot 2, q1 equals to q2, and weight flow rate equals to weight flow rate 2. Okay. Right, so we will continue with the next conservation. Okay, so the next conservation is called conservation of energy. Okay, or if you get back to the first page just now, conservation of energy is based on the first law of thermodynamics. What it means over here is the energy cannot be destroyed and it can be transferred from one point to the other. So we cannot destroy energy, but it can transfer from one point to another, and it can also transform. Okay, meaning the energy can change between electrical energy, it can become mechanical energy, from mechanical energy it can become flow energy and different kind of energy that we have in life. Okay, so the base of conservation of energy is the same as continuity, meaning if you have a piping system from one point to the other, for example like this, okay, point 1 and point 2, whatever energy that you have at point 1 should be conserved and it should equal to energy at point 2. So that's the idea over here. Okay, so the energy that will be involved over here is based on three different kind of energy. Number one is potential energy. I believe this is the one that we usually study in physics in high school. So we have potential energy. Number two, we have second energy, which is called as kinetic energy. Okay, and number three is called as flow energy. Okay, so potential energy, PE. Okay, the equation for it should equal to W multiplied by Z. Okay, W is weight, Z is elevation. Okay, and the meaning of elevation is, for example, if this is a floor and a body is positioned up here. Okay, all right. So the elevation is the distance between the body to the floor of our study. Okay, so this is elevation. All right. So if this is the base of the study, we can assume Z1 over here should equal to 0. And if this is the second point, we can get Z2 equals to certain number, for example, H. Okay, so that will be the elevation. Number 2 is kinetic energy. Before I forget, potential energy means the energy that you should get due to elevation. Okay, and the higher the elevation of the study, the higher the potential energy of the study. Okay, number 2 is kinetic energy. Kinetic energy is based on the velocity of the fluid. Okay, so the equation should be W V square over 2G. Okay, so W V square over 2G. So V will be the main influencer in this study. And the flow energy over here, we call it also as Fe, is the equation of it will be W P over gamma. P is the pressure. This should be rho times G. Okay. So there will be differences between potential energy, kinetic energy, and flow energy. Potential energy is based on the elevation of a system. The higher the elevation, the higher the potential energy. Okay. Kinetic energy is based on the speed or the velocity of a system or a fluid. The faster the fluid will have a faster kinetic energy. Flow energy is the amount of energy required. Okay. So in case we have point 1 and point 2. Okay. Flow energy is the amount of energy required. Okay. For example, to move a certain liquid from one point to the other. Okay. So the amount of energy required to move the flow, okay, or work necessary to move the element from one point to another point is called as flow energy. Okay, I think energy number 1 and 2 usually see in physics, but energy number 3, maybe this is the first time you are seeing it in fluid mechanics. Okay, so to provide the work from point 1 to point 2, it requires an energy. So the energy over here is this equation here. And if we combine everything, the total energy, okay, or we do it this way, is equal to PE plus KE plus FE. Alright. And if we do a comparison like this, based on this comparison, E1 is equal to E2, it means that total energy at point 1 should equal to total energy at point 2. So we should get WZ1 equals plus WV square over 2G 1, okay, plus WP 1 square over is equal to WZ2 plus WV square over 2G plus WP2 over Okay, so this will be total energy at point 1 should be equal to total energy at point 2. If you see over here, weight that is here in the study, okay, is the same for each one of them because the whole total weight that we have at point 1 should be the same as the total weight of fluid that we have at point 2. So because of that, this can be cancelled out. Right. So what happens when you cancel out all the W? Then you will get this very important equation in a fluid flow study, which is called as Bernoulli Equation. I believe if any engineer that studies the fluid flow, this will be the equation that will be very beneficial for them. Okay, and the Bernoulli equation says that we rearrange the calculation, okay, the equation to be P1 over rho G plus Z1 plus V1 square over 2G is equal to P2 over rho G plus Z2 plus V2 square over 2G. This equation over here is what we call as Bernoulli equation. Okay, so let me check. Somebody is asking question, I guess. Oh, why W2 kena cancel, sir? Saya tak faham. Sebab weight dia sama from left to right. Okay. I'll give you this slide like this. Okay, you can see weight of a fluid is the same. Okay. As I said to you before, weight at point 1 should be the same of weight at point 2. So the weight of fluid over here should be the same as the weight of fluid when it moves to the right side. Okay. Bermaksud flow daripada point 1 sampai point 2, kita based on the idea of conservation of mass. Mass from one point to another point should stay the same because we don't have any losses over here. Okay, so because of that, weight for each one of these items should be the same also. And because every single weight is the same, we cancel out all this weight over here. Then you will get the equation in terms of Bernoulli equation. All right. Does it answer your question?
Yes, sir.
Yes. All right. So P2 over here is called as pressure head. Or not P2. The P's element over here should be pressure head. Z will be called as elevation head. Okay, and V2 square over 2G is called as velocity head. Okay, and the unit for each one of them should be in meter. Okay, each one of them will have a unit of meter. All right, and why do we use the word of head over here? Because right now, what we are comparing between one point to the other point is not in terms of pressure. It is actually in terms of meter, in terms of height, or in terms of head. Okay, okay. Faham idea ni?
Faham, sir. Faham.
Okay, so that's the idea. So Bernoulli equation over here is based on head. Okay, so if you want to see Bernoulli equation in terms of pressure, okay, so ni in terms of head. If you want to see Bernoulli equation, I simplified by BE over here in terms of pressure. What you should do is you multiply every single thing over here with rho G. Okay, so what you do is BE in terms of head multiply by rho times G. Okay, so what will happen to this equation over here? It will become, okay, P1 plus rho GZ1 plus rho V1 square over 2 equals to P2 plus rho GZ2 plus rho V2 square over 2. So what we see over here, this equation, should be Bernoulli equation in terms of pressure. Okay, so what happened here is each one of this should have the unit of Pascal. Okay, hasil darab or the resultant of rho times G times Z1 should be equal to Pascal. So this one should be Pascal also, and this one should be Pascal also. So if in terms of head, we get it in meter. In terms of pressure, we will get it in terms of Pascal. Right? I believe when you are in high school, we see this one compared to the other one over here. Okay, so usually we see in terms of pressure rather than in terms of heat in high school. But for our study and calculation, it is much easier to study in terms of meter compared to studying in terms of pressure. Okay. So knowing that, we should get the basic idea of Bernoulli equation. So when we have a basic idea of Bernoulli equation, so what we need to do is, I will provide you with a certain question that we can do. Okay. But before that, I will talk to you about the limitations of Bernoulli equation. Okay, so this is really important for you to know, because our study later on will be based on this limitation. Okay, what does it mean by limitations of BE is the study of Bernoulli equation, number one, can only be valid for incompressible flow. I believe this is one of the question in the online quiz. So what does it mean by incompressible flow? It means we have no density change. Okay. All right. So number one, valid for incompressible flow. We assume the density of our study will not change at all. Water 1000 should be 1000 all the time. Okay. Number two, we don't have no mechanical devices between two points of interest or sections of interest. Okay, like just now, I showed to you from point 1 to point 2, we assume we don't have any mechanical work happening here, because if you do have mechanical devices, we cannot get the idea of conservation of energy over here. All right, because the energy has been transferred into different or transformed into different type of energy. Okay, number 3 is there will be no heat transfer into or out of the fluid. Meaning, you don't have any temperature change or anything in the system. And number 4, we assume we don't have any energy loss due to friction. Okay, so these 4 are the limitations of Bernoulli equation, meaning you will never get this kind of situation in real life. Okay, because whenever we have piping system from one point to another, it's hard for us to control, for example, the energy loss due to friction, because there will be friction over there. Okay, and when we have friction and the movement of liquid inside the pipe, there might be heat building up in the system also. And usually we will add multiple mechanical devices to help the fluid to flow. For example, we're adding up pumps, okay, and some part of the mechanical device, for example, turbine. And because of these 3 things that is happening, okay, that are happening, we might have a density change also in the system. So in reality, this system or this limitation will never happen. It means that every single one of them can happen in reality. So the Bernoulli equation is something that we study with the idea of no losses or no other things happening from 1 to 4 in the system, and it is easy for us to do calculation. What happens if we have losses in friction, addition of mechanical devices? So what will happen then is, from the Bernoulli equation, we will add up the losses and we will calculate the losses inside the energy equation. Okay, so based from the Bernoulli equation here, there might be some addition of losses. For example, at point 2, we add up the losses on this side. Or if we increase the pressure on one side, we add up on the other side. So it means we need to add up more parameters in the study. But for the basic or idea of Bernoulli equation, and from now on in chapter 3, we will assume these 4 limitations are there in the system. Okay. All right. So right now, I'll provide you with a simple calculation, and then the class will be done for today. And for the class on Sunday that is not available last time, I will do a recording on that, and we will do some study on different type of application that is related to Bernoulli equation. Okay, but for now, I will give you a simple calculation on Bernoulli equation. So for example, if you have a pipe and the pipe is designed to be like this, it means we have point 1 a bit lower here and point 2 is a bit higher at the top. Okay, and then okay, so we have A1 B1. Okay, A1 should be equal to 0.25 meter square, and then we have V1 equals to 3 meter per second, and then we have, for example, P1 to be 345 kPa. Okay, point 2 over here, might be we have A2 equals to, this is much smaller, so maybe we just provide you with 0.1 meter square, for example, and then we don't know the V2. Okay, V2 is not given in the question. Okay, and then P2 is not given in the question too. Okay, and then we have the elevation might be here, the elevation between these 2 points. Okay, so difference between these 2 points is the height should be 2 meter, for example. So now, assuming all the limitations are there, so we try to calculate what will be the pressure at point 2. Okay, to do this study, it will involve those 2 conservations that we learned just now. Okay, number 1, it will involve conservation of mass, and then we will do conservation of energy. So what happened here, if you see a question that looks like this, the flow is moving from bottom to the top, for example. So what we do is, first of all, we need to give ourselves the equation of Bernoulli, which is over here, we can just do P1 over rho G plus Z1 plus V1 square over 2G equals to P2 over rho G plus Z2 plus V2 square over 2G. And the first thing you need to do is find out what are the things that you have in the study. For example, pressure 1 is given, so good. Z1 and Z2, we know the pressure, the elevation, so we know the answer for this one. V1 is also given, great. What we don't have is P2 and also V2. So these 2 are the one that we need to solve. So how do you solve for V2? So to solve for V2, what we do is we use conservation or continuity equation. Okay, meaning we use this equation over here. Q1 should equal to Q2. So over this case over here should be A1, sorry, So what will happen here is we do A1 V1 should equal to A2 V2. So for this case, A1 V1 and A2 V2. So we want to find out what is V2. It is equal to A1 V1 over A2. So this should equal to A1 just now is 0.2. V1 is 3. A2 is 0.1. So V2 should equal to 6 meter per second. Alright, so this will be the velocity at this point, which is equal to 6 meter per second. So usually if we have an unknown V over here, if you know the V on this side and the area, you should get the V for the unknown V by using continuity equation. So practically when we are dealing with Bernoulli equation, you should do this first so that we can get the V for both sides. So right now, V is already calculated. So we only have one unknown here. So we should be able to solve this. So how do we solve this? Simple. This is just rearranging the equation. So if we rearrange it nicely, P2 should equal to P1 over rho G plus Z1 minus Z2, because we transfer from right to left, and then plus V1 square minus V2 square over 2G. Okay, and all of this are multiplied with rho G. So you will get P2. So we need to fit in the answer. So 345 times 10 to the power of 3 Pascal. Rho, assuming this is just water, so 1000 times 9.81. Okay, and then plus Z1 minus Z2. Okay, because Z1 is lower, Z2 is higher. If 1 minus 2, this should be a negative answer. Okay, so assuming this is, for example, the distance here, from here is 2 meter. Because 1 is lower, so usually what I will do is 1, because it is lower, it will become my reference point. So Z1 should equal to 0. Okay, so 2 is higher, so Z2 is equal to 2 meter. So that is what I do in the study. Okay, but if in case 0.1 over here, we know the elevation from the ground 1 meter, for example, 0.2 is 3 meter, so you can just use the number 1 and 3. Okay, but for this study, we don't have the elevation from 1 to the ground, we only have the difference in elevation. So because number 1 is lower, we design it as a reference, so Z1 is equal to 0. Okay, so P2 over here should equal to Z1. So Z1 minus Z2 is 0 minus 2 plus V. V1 should be 3 square. V2 is 6 square divided by 2 times 9.81. Okay, and every single one of them will be multiplied by rho 1000 and G 9.81. Okay, so P2 should equal to, let me calculate this. So P2 over here should equal to 311,880 Pascal. Okay. So the pressure over here is 311,880 Pascal. So that should be the answer for this question. All right. So if we can provide the energy equation here or Bernoulli, we can actually find any parameters that we have in here. Okay, as long as we only have one unknown. If we have two unknowns and the other one is V, we see V1 over here is available and area is available, should be we have a good calculation on continuity equation and we can actually find V2. So for this question over here, the P2 is 311,880. Okay. One important thing that you need to know is pressure for our study, P1 or P2, usually is studied in terms of gauge pressure. Okay. So usually is studied in terms of gauge pressure. Okay. So this is not manometer. Usually if manometer, we will study the absolute pressure. In chapter 3, okay, so this idea over here is used, meaning all the pressure that we will be using starting from now should be in gauge pressure. If you want to find out the absolute pressure, you just have to add the PATM, that's all. Okay. So that will be the important things that I will cover for today. And then the next thing that will be covered, I will cover it in recording, I